Hello, I'm Haiying. Welcome to Feature Extraction and Feature Engineering. In this video, we'll discuss data transformation, focusing on log transformation, power transformation, and box-Cox transformation. Log transformation is a mathematical operation of taking the logarithm of a variable. Two frequently used log transformations include natural log to the base of e and the common log to the base of 10. Here are some examples of log values. Log 1 equals to 0, log 10 equals to 1, log 100 equals 2, log 1000 equals to 3, log 10,000 is equal to 4. The log function transforms a large value. This graph illustrates how the log function compresses the high numeric range from 0 to 10,000 to 0 to 10. Log transformation is a powerful tool for dealing with positive numbers with a heavy-tailed distribution. The logarithmic function and the exponential function are inverse operations of each other. Benefits of log transformation. Log transformation can help make skewed distributions closer to a normal distribution. This is beneficial when working with analysis that assume normality, such as linear regression. Heteroscedasticity or non-consistent variance across different levels of variable can be problematic for statistical models. Log transformation can stabilize variances, reducing the impact of outliers and making the data more homogeneous. Linear models often assume a linear relationship between variables, which may not be the case in the original scale. Log transformation can linearize certain relationships, enabling the use of linear models and simplifying interpretation. Outliers can disproportionately impact certain analysis. Log transformation can compress the range of values, reducing the influence of extreme values and making the data more robust. Some analyses assume specific distributional properties, like normality. Log transformation helps align the data with these assumptions, improving the validity and reliability of statistical analysis. The visualization describes the distribution of reading time and shows the benefits of using log transformation for skewed data. The left figure shows that the distribution of reading time is right-skewed with a long right tail. The right figure is a log-transformed distribution, a normal distribution. This distribution comprises a long tail at the high end of the distribution, creating a shorter tail. At the same time, it expands the low end into a longer head. Take the relationship between reading time and reading score as an example. It is clear that reading time is heavily right-skewed and is likely to have significant heteroscedasticity in the regression equations. However, by applying a log transformation to reading time, a linear relationship becomes apparent. Why? Because the Pearson correlation coefficient we used to measure correlation tests for a linear relationship between variables. And the Pearson correlation coefficient conforms to the standard T distribution only when the two variables follow an uncorrelated bivariate normal distribution. Notably, the Pearson correlation coefficient between two variables that are not independent can be zero if the relationship between the variables is nonlinear. In this way, the application of data transformation facilitates more straightforward statistical inference, such as t-test, ANOVA, or linear regression. If the data displays significant skewness, the use of aforementioned statistical inference becomes impractical. A power transformation is a mathematical operation applied to a set of data by raising each data point to a specific exponent. The general form of a power transformation is given by y is equal to x to power b, where b is an exponent and x is base, the original data point. The frequently used power transformation includes square root transformation and cube root transformation. This is an example of the reading time variable, showing both the original time and the transformed time. In statistics, a power transformation refers to a family of functions used to establish a monotonic transformation of data through power functions. This technique serves the purpose of stabilizing variance, promoting a distribution that resembles normality, enhancing the validity of measures, and facilitating the data to adhere to specific assumptions. In this example, square root transformation was applied to reading time. Reading time distribution looks more normal. Box-Cox transformation is a family of power transformations that are applied to stabilize the variance and make a dataset a more closely normal distribution. It's named after statisticians George Box and Sir David Roxby Cox. They collaborated on a 1964 paper and developed this technique. Box-Cox transformation can improve the predictive power of your model because it cuts away white noise. We use y to represent the transformed variable, and x is a target variable. The parameter lambda in the Box-Cox transformation controls the type and strength of the transformation applied to the data. Different values of lambda result in different types of transformations. If lambda is 1, there is no transformation. If lambda is 0, it's a log transformation. If lambda is 0.5, it is a scaled and shifted version of the square root transformation. If lambda is negative 0.5, it is an inverted square root transformation. Let's see how the transformation works. If lambda is 1, we have a linear transformation, a straight line, simply shifting x to the value x minus 1. If lambda is 0, it is a logarithm. If lambda is greater than 1, it is concave. If lambda is smaller than 1, it is convex. Pros and cons. If interpretation is your goal, then the Box-Cox transformation may be a poor choice. If lambda is a non-zero number, then the transformed target variable may be more difficult to interpret than if we simply applied a log transform. The Box-Cox transformation usually gives a median of the forecast distribution when we revert the transformed data to its original scale. Occasionally, we want the mean, not the median. Log transformation is applicable only to positive values. Square root transformation is applicable only to non-negative values. Box-Cox transformation is generally applicable to positive values, but it may have constraints based on the selected lambda parameter. It's common that the data contains zeros. In this case, we can add a small number to the data so that we can perform log and the box-Cox transformation. Log transformation is typically applied to positively skewed data with positive values. If the data contains zeros, we can add 1. If it contains negative values, we can add a number to make all the numbers positive. Final thoughts about normalization and transformation. From the perspective of purpose, data normalization is to scale numerical features to a standard range. It ensures that all features contribute equally to the analysis, prevents one variable from dominating others due to differences in scale, and facilitates convergence in certain machine learning algorithms. Data transformation is a broader concept with various purposes. It can be applied to stabilize variance, handle skewness, or make the data more suitable for specific statistical analysis. Normalization alone does not address outliers. Extreme values can still have significant impact on the scaled data. Some transformation techniques, like the log transformation, can soften the impact of outliers by compressing the range of extreme values. Normalization does not handle skewed data distributions. Data transformation, like log transformation, is specifically designed to handle skewed data by reducing skewness and making the distribution more normal. Data normalization typically assumes that the data follows a roughly normal distribution. Data transformation can be applied more flexibly depending on the specific transformation used. Some transformations, like the box-Cox transformation, are designed to make the data more normal distribution-like. Thank you. See you in the next videos.